whoever you are, evangelistically Everettian, or still holding out for hidden variables. Hello. One reason I'm usually so reluctant to discuss quantum mechanics concerns something that Albert Einstein said. He was famous for saying, among other things, that if you can't explain something simply, you don't understand it well enough. Another reason to shy from the topic is because Richard Feynman, the famous quantum physicist, declared that if you think you understand quantum mechanics, you don't understand quantum mechanics. However, it recently occurred to me that if you take both of these scientific giants at their word, a passionate non-authority like me has very little to lose. So here goes. Either I can't explain it simply and expose my blameless ignorance, or I can, in which case I still can't claim any kind of understanding. It's with these reassuringly bleak odds that we embark on our quest to discover some small island of clarity amid my personal ocean of quantum incomprehension. If a subject like quantum mechanics has all the experts confused, why should it matter to us laypersons? I like to think it's because reality is a race we all have a horse in. It's a pity, then, that our basic intuitions about reality pose the first problem. To demonstrate, who can visualize just how far the moon is from Earth? I thought I had a pretty good grasp of this until I found a way to create a scale model in my own living room. To do this, put a basketball on the floor. That's going to be planet Earth. Now walk away from it 30 paces heel to toe. Where you stop, lay a grapefruit on the ground, or any similarly sized orb that you happen to be carrying. This is about the scale of the Earth-Moon system, with the grapefruit representing the moon. Standing back and beholding this model from our God's eye perspective, that grapefruit placed 30 feet away from the basketball looks pretty small and remote. Staring up at the moon in the night sky, as we are all quite partial to doing from time to time, you wouldn't think that those were the kinds of scales involved. The moon seems much closer and more intimate with the Earth, at least to me. But this is far from the only time that our intuitions can be shown to let us down. It's also all but impossible for us to grasp that there are far more molecules in a glass of water than there are glasses of water in all the world's oceans. Human intuition works best when dealing with sizes between insects and houses, and events spanning seconds to decades. Beyond these limits, what we feel to be true is a pretty lousy guide. Now consider this. Nobody can hope to reverse engineer a desktop computer by studying its operating system. The mouse pointer, start bar, and recycle bin tell us nothing about the microchips and circuit boards that generate them. These are functional tools to help us navigate a virtual world. Similarly, everything we see around us, horses, snooker tables, people, the moon, may be phenomena that emerge from utterly different underlying physics. By subverting and augmenting our feeble biological senses, science allows us to dig through layer after layer of these emergent effects to uncover what's really going on beneath. And quantum mechanics is as deep as we've dug so far. Quantum mechanics, as a remote outpost of scientific understanding, seems to be one run by nutters. Gazing out from this quantum encampment, the view in every direction appears bizarre, counterintuitive, and impenetrable. Which way should we go? Who should we be following? Thankfully, the scientific process has a built-in guidance system. For a boost in reputation, scientists will enthusiastically try to prove each other wrong. All that constrains them is the material world. By relying on empirical facts that can be tested, science auto-corrects itself, allowing good ideas to persist while the nonsense gets purged over time. Reality itself keeps science on track. It's to be expected, then, that the scientists out here on the front line of our current understanding often get proven wrong. In the past, Isaac Newton must have seemed like a maniac, and perhaps he was, but his ideas about forces and motion stood their ground while competing theories withered away. Science advanced with nature's blessing. When Einstein took the reins, huge progress was made, even though what he claimed sounded like drooling madness. With the powers of Newtonian physics and Einstein's relativity combined, exotic notions like bending time, black holes, and gravitational waves could be investigated and shown to be real. We realized that a person's place and motion in space directly affected their accounts of time and distance. Intuitions be damned. To put this knowledge to use, in satellite navigation, atomic clocks, and supercomputers, our everyday picture of the world had to change. Space and time had to be fundamentally interwoven. Einstein called this space-time, and it was space-time that told solid matter how to move, while matter caused space-time to curve. This is mind-blowing stuff, but it's old news. To fully explain our familiar, everyday world, scientists needed to pick apart the space-time canvas on which reality is painted. As we saw last episode, it's from this bizarre quantum fabric that the universe came into existence. So let's leave Alfie and Isaac, Team Classical Mechanics, gazing out into space for the moment. We need to return to quantum mechanics, peering down at reality on the very smallest scales. If we're ever to conceive of how ultra-small events play out over infinitesimal fractions of time, all of our preconceptions about how things work need to be shelved, or at least put on aeroplane mode. Perhaps the hardest thing about quantum mechanics, certainly the most contentious, is interpreting what the experiments are telling us. It's almost impossible to describe what's going on without resorting to hopelessly flawed analogies. A snooker ball moves from one position to another when it is struck, following a predictably smooth path across the snooker table. This is the kind of classical world that we can easily imagine. When subatomic particles like electrons or photons of light change position, scientists can't agree on exactly what happens. Analogies crumble. Curiously, this doesn't hinder scientific progress as much as you might expect. The reason is quite a practical one. I am perfectly capable of using a microwave oven, a tremendous source of personal pride, without the faintest idea of how it works. Nobody knowing how quantum mechanics works hasn't stopped it becoming the most accurate theory in all of science. When it comes to making predictions about what reality will do, the undisputed champion is a set of equations called quantum field theory, or QFT to its friends. Experiments designed to explore the ultra-teeny-tiny subatomic events in our world consistently pan out the way that QFT suggests they will, to 14 decimal places. That's an accuracy akin to measuring the distance between Los Angeles and New York to within a single human hair. Nowhere else in all of science does theory map onto measurement so well. But remember, much like relativity, quantum field theory models reality in a way that we can't begin to visualize. Quantum field theory not only challenges common sense ideas of cause and effect, but totally gaslights our impression of locality. Locality is what it means to be neighbours in space, where one object is in relation to another. QFT suggests that everything is ultimately composed of interacting energy fields. These fields fill all of space and vibrate relentlessly. Certain vibrational frequencies give rise to the particles of matter that we observe, the protons and neutrons and electrons responsible for atoms. Where no particles exist, the field is still there, just in its lowest possible energy state. These ain't just purdy words. Out of the calculations come radioactive atoms, shimmering polar auroras, solid tables that you can park your coffee on, and functional microwave ovens. We can take the theory and use it practically, from equations to predictions to experiments to mobile phones. Proof of the equations evidenced by the world as we observe it. Because everything in the world is ultimately quantum mechanical when you look close enough, composed of subatomic particles obeying the rules of QFT, comparisons to global distances and colliding snooker balls can only take us so far. Because the entire universe was born from a quantum-scale event billions of years ago, we should really try to describe the world we experience from the quantum realm up. New layers of physical laws, including the much-loved classical mechanics of Newton, emerged as the universe grew, eventually allowing us to detect the Big Bang and put people on the moon. These outermost layers, where Einstein set up shop, tend to suggest that we can measure things with certainty. Newton surmised that if you could know everything about the world as it is, right now, in its current state, you could work out the state of the world at any point in the past or future. That is, if you could know all of the particles, their motions and energies and directions with precision, you could determine what the universe would look like at any other point in time. He was quite confident about this, but the equations of quantum mechanics strongly disagree. They insist that only the probability of a certain outcome can be predicted, albeit with astonishing precision. The probability distributions, or wave functions, are all that can be assumed to actually exist. Not because of our ignorance, not because there are supernatural forces at play, not even because our computing power is woefully limited, but because uncertainty is a fundamental part of our universe. If diffuse clouds of chance are our best description of reality, why don't we notice? The answer lies in the fact that there are many interacting, cascading events all happening simultaneously in the universe. Who knew? By treating clumps of matter as individual objects, like snooker balls bumping into each other, classical mechanics provides a good working approximation of how things behave. Shrunk to the size of electrons, those snooker balls can no longer be thought of as possessing separate positions and motions. Each ball in isolation would behave according to its own wave function, a summing up of more or less likely outcomes. Bizarrely, if you were to incorporate the entire snooker table and everything on it, the whole system would still only act in accordance with a single wave function, now encompassing all possible outcomes at once. This superposition of all snooker ball configurations and interactions really exists. It's what physicists call entanglement. Although we could no longer predict where any one ball was going to be, once an observation was made, you could know the positions of all entangled balls simultaneously. This is due to the fact that only one wave function describes the whole snooker table system that we're considering. Now, I know what you're thinking. You could happily listen to me talk all day about entangled balls, but how does this actually translate to the world that we see? If we zoom back out to more familiar human dimensions, the reason that we can measure the position of a coffee cup, or a person, or a planet is because all their constituent particles are entangled with the rest of the world. Countless multitudes of quantum particles interacting with each other gives the overall system only one probable location. It's as if all the large, visible objects around us are constantly being monitored by all the photons and subatomic particles that are bumping into them. It's this constant environmental bombardment that grants large, entangled objects, like my computer and the moon, a single classical trajectory. This idea may be a headache, but, for better or worse, you can blame all of those light beams and air molecules bouncing off you for your not being everywhere all at once, as a diffuse probability cloud. It is this effervescent foam of quantum interactions that's keeping track of where you are, forcing your personal probability wave to manifest as a uniquely sexy event in space-time. Stop thinking about balls. So, this addresses our apparently definite position, but doesn't explain why objects only interact when they collide. In other words, why do particles only touch when they occupy the same position in space? Why not when their velocities are the same, or their charges? What is so special about the idea of position that allows a causal exchange? If this question seems stupefyingly obvious to you, unworthy of further consideration, I blame myself. I readily gave in to discussing quantum mechanics with reference to classical snooker balls. Rookie mistake. We completely overlooked the fact that to understand the universe, we need to know where spatial dimensions actually come from. And here is my mind-blowing fact of the day. Scientists have learnt that locality can't be a fundamental feature of the universe. We can't just take the existence of space with particles in it for granted. A particle's location must emerge, a property of the interactions permitted by its wave function. Trying to keep it simple, and failing, instead of saying two things will interact when they are close to each other, we have to reverse our thinking and say two things are close to each other when they most strongly interact. This ability to interfere is how we gauge whether two particles are local to each other, and not the other way around. Thinking quantum mechanically, distance becomes a summary of fundamental physical interactions. The emergence of separate locations in space comes from all of those entangled interacting wave functions. Kudos if you're still listening. Quantum mechanics is a wild ride, but it underpins everything. Once we can say that degrees of entanglement are what define different locations in the universe, our goal becomes extracting the full geometry of space-time from one single wave function. Understanding how we get from entanglement to general relativity via a purely emergent space-time would be a monumental achievement. One I'm not even going to attempt to discuss. Yet even this wouldn't be the full story. Remember, nothing in quantum theory overturns what we already know from Einstein and Newton. New science builds on that which came before. When Einstein discovered that space-time was curved, that didn't mean that Newton was wrong, it just took our understanding a layer deeper. The success of QFT doesn't imply that Einstein is mistaken either. It just forces our eyeballs uncomfortably close to the computer screen. The data and the physics is conserved at every level. Anything that we learn next must accommodate what we've discovered to date, not replace it. The impression that science keeps reinventing itself, or that science is pointless because it keeps changing, is a common misunderstanding. It doesn't. What changes is our conception of the universe and ourselves. Findings from different areas of research have to be reconciled, not rejected. This means that science gets less and less room to maneuver as more and more data comes in. Reality gives knowledge a forward direction. The science of the past wasn't wrong, it just wasn't a complete picture. The same will no doubt be said of today's science in the future. Now that we've grappled with the fabric of reality and have at least some appreciation of the canvas on which the cosmos is painted, we can turn our attention to subjects that I feel a lot more comfortable talking about. Let's try and wrap our feeble mortal minds around the scale of the universe itself. Because why not? Stop thinking about balls.